Welcome everyone to this Nordic partner webinar. Today we have with us Ignion, and I'm very excited to see what Joma from Ignion is going to tell us and explain how to embed a compact antenna in your global cellular IoT product. So my name is Petter Myhre, and I work. I'm head of product marketing at Nordic Semiconductor. And with me today, we have Joma from Ignion. Maybe you want to say a few words about yourself, Joma?
Well, first of all, thank you everybody for being here today. It's a pleasure from Ignion, and thank you, Nordic, for inviting us. And my name is Jaume Anguera. I am CTO and founder at Ignion.
Thank you, Joma. Then over to some practicalities before we get into the presentation. The duration of this webinar will be approximately 60 minutes. Please ask questions, but please do that in the top of the right sidebar. All questions there are anonymous, and I encourage you to keep them relevant to the topic. We will answer questions towards the end. So please be patient, and we will answer questions in the end. I also want to say that the chat is not anonymous, and please do not use that for questions. And if you have more questions or your questions didn't get the answer you wanted, you can reach out to Nordic on DevZone or Ignion by sending an email to support@ignion.io. And as always, a recording of the webinar will be available together with the presentation at webinars.nordicsemi.com. Try to get that out tomorrow, but it might also be Friday. So then it's over to you, Joma.
Okay, thank you, Peter. So welcome to this presentation on how to embed a compact antenna for your global cellular IoT product. It has been prepared by Ignion. You are in the correct webinar. We changed the name of the company from Fractus Antennas to Ignion. You can guess Ignion comes from the word ignite, and is the purpose of our virtual antenna technology is to ignite your connectivity and accelerate your innovation of your IoT device. This will be the agenda. First of all, we are going to see why virtual antenna changed the deal, which are the parts of an antenna system based on virtual antenna, and how we can embed with very simple steps virtual antenna into an IoT product. Then we will see some tips on how to combine virtual antenna products with Nordic transceiver. Then we will see some electronic design automation tools to give some guidelines on how you can use some software to embed by your own the antenna system into your device. And at the end, we are going to compare virtual antenna with other technologies, and at the end, some conclusions. Well, you might guess this is a chess game, and I hope you remember the nice battles with Kasparov, the master Kasparov, and Deep Blue. And the very first movements at chess are very important, yet very simple. And the same happens with antennas. If you are designing IoT devices with antennas, the first consideration is to have the antenna in your device. If you want data into the cloud, connectivity, range, battery life, consider always the antenna from the very beginning. Why antenna? Why virtual antenna? It's attractive for the IoT market. In here we have an evolution from the very first external antennas, the monopoles, which are easy to rake, they are big enough, they are very big. And then we have this kind of internal antennas with complex shapes, with volumes that are around 1,000 millimeter cubes. The big breakthrough we have with the apparition of virtual antenna, where we can see that it's about only 100 millimeter cube. In fact, you can see my finger. This is one of the products for IoT operation. It's only 125 millimeter cube. It's a cube of only 5 by 5 by 5 millimeter. So besides being small, the virtual antenna components, by the way, they are called antenna boosters. They are not only small, They can be multi-band and even multi-radio. They can operate at several radios at the same time. And they are off-the-shelf products, so ready to use, and pick and place. So they can be assembled into a PCB like any other chip, like an amplifier or a filter, which is very convenient for mass production. This technology is already adopted in the market in more than 25 million devices for fleet management, modules, smart trackers. You can see here an example with the Nordic Semiconductor. It's the Thingy 91 with a small footprint of only 50 by 50 millimeter for narrowband IoT, LTE-M plus GPS with this red antenna booster that you can see in this graph. We have in blue dots some antennas for the same operation, and in red we have antennas from the virtual antenna family. In particular, the Thingy 91 this is length of the antennas, this is width of the antennas for the same operation. You can see that this has the smallest footprint of the device, as well as very small antenna with very small footprint and with only 1 millimeter high. So this is the reason why we could work with Nordic Semiconductor to fit in this small antenna to have this multi-band operation at LTE as well as GPS. So why virtual antenna changed the deal? Well, the main important feature is that it's not the antenna which dictates the frequency of operation, but we as IoT designers, we can freely choose the frequency of operation. So imagine we have one device with different form factors. We don't need to change for every form factor the antenna. We can use always the same antenna booster, which is shown in red, and the only thing we need to change from one device to another device is a matching network, which is a combination of LTE-M components, inductor and capacitor. Even if you want to change the frequency of operation from one device to another device, again, we don't need to retune the antenna by changing the component or doing a new antenna from scratch. The only thing we need to do is to change a matching network. And this, by the way, it's easier and faster than designing a customized antenna. Let's see what is the architecture of a virtual antenna system. So besides the booster, this tiny component here, we have the matching network, which is a combination of LTE-M components together with the transceiver. At the end, the matching network, it's the part of the electrical circuit that allows us to make the overall system to operate at the frequency we want. So we have very much flexibility. So you can see that the designing of antennas, it's radically different from the old way that it's designing a new geometry. In this case, once the component is fixed and once the antenna booster is determined, the intelligence is put on the matching network. And then we have the transceiver, the Nordic transceiver, that should be as close as the matching network as possible. And finally, a very important part of this architecture is the ground plane of your device. You have your device, then one part of this device is the ground plane. At least one of the layers of your multi-layer PCB is a continuous ground plane, which is useful for this to radiate efficiently. So by properly selecting the antenna booster in the right position in the matching network, we can end up with a system that has a very tiny component, 10 times less than conventional antennas, yet providing frequency operation at any IoT frequency standard. Let's illustrate how a matching network can select the frequency of operation. So we have an antenna booster in a PCB. By properly designing a matching network, we can go from single band operation to a multi-band operation, and even a multi-band including more bands at LTE. So you can see that the approach or the intelligence is not only put on the antenna, but when the antenna is done, all the design process is in the matching network. And the good news about this is that this matching network can be designed very easily and very fast using microwave simulators. So we don't need to worry about on how to design these matching networks. because the software will do it automatically for us. Another consideration about the device or the ground plane size of your device, this is very important because it impacts the efficiency. At the end, the efficiency of the antenna system is the ratio between the transmit power into space over the output power of your transceiver. So the 100% is the best case. And you can see that in the low frequency regions, 700, 800, and 900, for small PCB areas, this is 10 centimeters square, to large PCB areas, you can see that there is a dependency on the efficiency. So for small ground planes, the efficiency may be 30, 40%, and it can grow up to 80, 90% for large PCB. In the high frequency region, so above 1.6, 1.7 gigas, this is not as critical. So here the conclusion is that the device size should not only be chosen because of marketing purposes, but also driven by engineering results, taking into account that the ground plane of the device may impact the performance of the antenna system. And at the end, it's going to impact the battery life, the range, the connectivity. Let's see how we can embed virtual antenna with very basic steps into an IoT device. This is very basic steps. The first one is, well, to select the best antenna booster and place in the IoT device. Usually, as a rule of thumb, the corners of the ground plane are the best position in order to maximize the bandwidth and efficiency. We invite you to visit this video. It's a 3-minute video that provides more details on how to allocate the antenna booster in the ground plane of your device. Once we have that, the second step is to allocate the matching network so as to maximize the transmitted power from the transceiver into the antenna. And again, you can visit these videos to get more details. And at the end, what we need to do is to check it out that, well, everything is working. So you have the antenna booster, you have your matching network, and then you can add this 50 ohm transmission line for testing purposes with your vector network analyzer, just to be sure that the efficiency, the S11, the SWR, has been adjusted correctly into your frequency bands. So with 1 to 3 steps, it's easily to embed a virtual antenna into an IoT device. Let's have some examples. In this case, you can see this is the Thingy 91, and in red we have the antenna booster, the trio antenna booster. You can see that it's always at the corner of the ground plane. At least one of these layers of this multi-layer PCB, it's a continuous ground plane. You can see in this picture a little bit better. You have the antenna booster in red, then a feeding line that goes to the electronics with the matching network and eventually reaches the Nordic transceiver for LTE and as well as GPS. So always, as a rule of thumb, feeding the antenna booster at the corner of the ground plane provides the best bandwidth and efficiency for your device. Second is to design a matching network. The matching network gives the flexibility to have operation at any frequency we want. For example, in here we have in yellow we have the ground plane of our device. We have an antenna booster, and without any matching network, we can have an impedance that is very far away from the center of the Smith chart. But with the addition of a matching network, in this case a very simple matching network, we can change the impedance to be very close to the center, and then we can get a very good S11 response and a good efficiency. So you can see that we have a lot of flexibility, because at the end we can freely choose the frequency we want to operate by designing the proper matching network from single band to multi-band. And this is very flexible because you can do at any time of the design process. Perhaps you are very close to certification and you are adding a new material on the device because some plastic covers and the antenna system get detuned. You don't need to design a new antenna. You don't have a bottleneck on the antenna. The only thing is to design, to retune the matching network, and again, you have response, and you are sure to have your device certified. Let's see now some tips on how we can combine the Nordic transceiver with virtual antenna products. In red, we have some of our virtual antenna products with different footprints. In particular, the first three ones, this is a cube, this is called RAN, and this is called bar. These boosters, these antenna boosters, are suitable for providing operation between 800 up to beyond 6 giga. Then we have this one here, it's called the trio, which is very particular and very convenient for triple radio operation. It can have LTE plus GPS plus Wi-Fi, as we are going to see now in more detail. This here, the all, is very similar to this one here, but it can go down for 700 megas to include some of the narrowband IoT frequencies. Then we have another multi-radio antenna booster. This is called Duo, and it's for dual band operation simultaneously for GPS plus Bluetooth. And finally, we have this is a 1MX10. It's only 7 millimeter length. It's pretty, very small. And it's for multi-band operation as this one, but with more narrow bandwidth. Perhaps it's for single band in the low bands and some bands in the high bands. We invite you to visit our application notes in our webpage. It's plenty of technical data on how the ground plane may impact the efficiency of your device, so you can get some guidance on how you can start from the very beginning to determine which PCB size or which ground plane do you need to have enough bandwidth or enough efficiency. Let's have some examples. Let's have a look at some examples. Here we have this antenna booster. It's called the RAN MX10. It's only 12 millimeter length. And here we have the layout for a matching network. And the transceiver, the Nordic transceiver, the NRF9160, that should be very close to the matching network. Try to minimize the feeding line, the 50 ohm feeding line in red, to the matching network in order to avoid any interference or any losses. When the matching network is properly designed, in this case, it's a combination of 5 components, SMD components, size 0402 are the typical components we recommend from Murata, for example, tight tolerance and high Q. These are typical components available for most of the component manufacturers. Sometimes you can use 0201 and 0603 SMD, but usually the most common is 0402 high Q tight tolerance. You can see that we can have this multi-band response. In blue, we have the efficiency. This is measured efficiency on the evaluation board in the low frequencies of narrowband IoT and in some frequencies of the high bands of the narrowband IoT. And you can see again the antenna booster and the feeding line close to the corner of the ground plane. And some clearance area. This part here is a clearance area that should be free of any component, any tracing line, the battery. It should be free of components. Imagine you have some space constraint and you want to reuse this space for perhaps putting sensors, humidity sensor, light sensors, accelerometer, and you want to reuse also this part of the ground plane, you can do it. And we can have very small clearance area. In this case, it is represented by the letter F. If F is 60, it means that we have full clearance. But if F is equal to 20, it means that we have only 20 millimeter by this distance, which is 11 millimeters. So it's only 20 by 11 millimeter of clearance area plus this small antenna booster. And you can say that impact is not that critical. For the full clearance, we have the blue line for low frequencies and high frequencies. And in orange, for the smaller clearance, we reduce a little bit the efficiency, but still we provide good efficiency. So this has auto flexibility. And again, antenna booster, feeding line to the corner of the layout of the matching network, and the transceiver NRF9160 as close as possible to the layout of the matching network. More example, imagine you want to go down to 700 megas for some frequencies of the narrowband IoT, LTE-M. We can use the Trio MX10. This red component, it's only 30 millimeter, but 1 millimeter high. It's very thin profile. With the matching network, in this case, it's a combination of several components, and with the transceiver. And again, the transceiver very close to the matching network and feeding line close to the ground plane, which is this area here. The clearance area, it's all what's inside the red rectangle. Everything outside the red rectangle can be ground plane and other layers for all the electronics. And we can provide with that very good efficiencies across many frequencies. Also, we can use this, the 1MX10. It's very small, it's only 7 millimeter. In this case, we sacrifice some of the bandwidth in the low bands, but for some applications, it's enough, and still having some frequency bands in the high frequency region. And again, this can be combined with a transceiver, nRF9160, together with the matching network, the feeding line close to the ground plane, and the clearance area should be free of any component, any trace, any sensor, not only on this side, but in any layer should be free of any component in order not to interfere with the antenna and impact the efficiency. Let's move to the multi-radio examples. In this case, we want to have a system that is for narrowband IoT, several bands of narrowband IoT, plus GPS, plus Wi-Fi at the same time. So one approach, the obvious approach will be, okay, let's have some transceiver, let's have one antenna booster for narrowband IoT, another for GPS, another for Bluetooth. So we need 3 separate antennas in 3 different positions with long tracings. So this works, obviously, but you are occupying some space of your IoT device, and for some IoT devices, the ground plane is small, so we don't have too much space for putting too much things. So the alternative and the unique and component that is in the market for 3 radios at the same time is the Trio. The Trio provides simultaneously operation at narrowband IoT, some frequencies of narrowband IoT, plus GPS or any kind of global navigation satellite system, Beidou, GLONASS, even Galileo, and Wi-Fi. So you can see that this is a very compact with only one Trio, only one part. We can do everything. So let's illustrate how we can bring this into practice. You can have a look at this application note for more details, but here we have in red the Trio. It's a triple port, so one port here with one matching network for LTE, narrowband IoT, and the transceiver nRF9160. It has another port, which is for receiving GPS signal. It has a feeding line to the matching network and to the port of the Trio antenna booster. And then for Bluetooth, we can use another transceiver, the latest transceiver for Bluetooth or Thread or Zigbee, which is the Nordic 5340. And you can see that we can provide simultaneous operation at mobile bands in green, at GPS in red, and at Bluetooth in gray, with only one part. Let's move to another multi-radio solution. In this case, is with the Duo. The Duo can be useful for simultaneous operation at GPS or GNSS, GPS, Beidou, GLONASS, in addition to Bluetooth. So we have here the transceiver for the Nordic transceiver with the matching network, and then we have the transceiver for LTE plus GNSS connected to the matching network for GPS, and then we have the transceiver which is connected to LTE to provide operation at several bands of narrowband IoT. The Duo, it's a very compact antenna. It's only 7 millimeter length by 3 millimeter width and 2 millimeter high. And it has no clearance beyond the antenna footprint. So you can have all ground very close to the antenna footprint, and the only ground clearance you need is the same as the antenna footprint. So you can have more electronics packet close to the antenna, because you don't need having a clearance area. And for some particular situation where the ground plane is very small, yet you need to provide operation at several bands, which is the case, by the way, of Thingy 91. It's only 50 by 50, and we need to provide operation from 700, 960 to 1710, 2200 plus GPS. We end up with a solution that, since with a passive matching network was not enough to provide enough performance, we decided to split the problem into a small matching network. So for instance, you can see here what we have is the antenna booster, which is here, the transceiver, which is here. It transmits and receives narrowband LTE signal. It receives GPS with two switches that can be controlled with the transceiver, either with GPIO interface or even with RFFE protocol. It can support both the transceiver. So the transceiver controls the state of the switches. So in this case, the signal travels through this path, and we have a very simple matching network, only matching this frequency range. So it's a very simple matching network, only one or two components, and so forth. So when the transceiver changes state, we have another matching network to provide operation in this particular frequency range, both for transmitting and receiving, and so forth and so forth. Okay, and for GPS, very similar. Once the signal is received by the satellite, the signal it's matched with this matching network here, a very simple matching network. It gets the low noise amplifier before entering the transceiver. This is highly recommended, a low noise amplifier. The signal gets amplified, and this is a 50 ohm amplifier. It gets amplified and reaches the transceiver. So all these lines here should be 50 ohm coplanar waveguide. If you want more details on the design of this sensor, which is plenty of sensors in this small platform, please have a look at our webinar in YouTube, where you will get a lot of technical tips. Let us share with you some of the electronic design automation tools where you can use virtual antenna products to design your own IoT devices. And if you don't have those tools, also we can provide that help. So let's have a look at three particular tools. And these tools are useful depending if you are in the proof of concept phase or you are in the design phase. And for other cases, if you don't have these tools, well, no worries, because we can also provide this support in the proof, the design, and even in qualification. Let's have a look at libraries. What is libraries? If you are familiar with a microwave simulator, so dealing with amplifier, filters, diodes, inductor, and capacitors, you have all this kind of stuff, but you don't have an antenna. Antenna, it's 50 ohm resistant, but this is not true. So for the first time ever, we have embedded, together with our partners, Cadence AWR software, the microwave office software, for the first time ever, a library that contains a set of PCBs with different sizes and with different antenna boosters. So if you have in mind a design and you want to check if that device is going to meet the requirements of bandwidth, you have a tool from the very beginning to check with the simulation if the device you have in mind with the platform and the antenna can get enough performance, enough bandwidth. And if not, you can react very fast and take action. And that action can be done at the very beginning of the project, in the proof. While you are in the development, to change the platform size, this is almost forbidden. It's you will put the project at risk. Okay. Let's have some example. Imagine at the very beginning, you want to design a device like the Thingy and say, well, my device should be 50 by 50. Can I work with this size to provide operation at some bands of LTE? So for sure, you will have a ground plane in our library that it's very close to your ground plane or to your device size. If not, you will choose something that is very close to your device size. Once you have it, you will say, okay, I need LT band 700, so I will select the trio, which is convenient to provide multi-band response across several frequency ranges. So this is it. This will be my library. My library should have the trio, this ground plane, and the overall size is 50 by 50. So we go to library. This library is open in this link address. It's open. You can use it. There is a user manual that explains step by step how you use this library, either for Cadence Microwave Office, or if you are using Opteni or any kind of software you can download, because at the end, this library is nothing more but an S parameter that contains the S parameter of this device without any matching network for a huge frequency range from 0.6 up to 10.6 giga. So now you are ready to test your matching network to see if you can get enough performance of your device. Let's have a look at this example. Imagine we have this device and we want to use this antenna booster by any reason. Again, we have the corner, and we want to have operation at several bands of the LTE spectrum. And you specify a target. For instance, my S11 or SWR, my S11 should be less than -6 dB or -7, -8. This is flexible. And nothing else, because the software will tell us the matching network if it's possible to get this bandwidth. If not, the software will provide a matching network, the closest matching network to achieve this target. Let's have a look. Let's have a look at this video that illustrates the process. This is the Cadence Microwave Office. It's a library that it's already integrated into the software. So beside capacitor, transistor, filters, you have this library. Very soon it will be Ignion. We are now changing the name of the company, so it will be Ignion. And you have, for instance, a set of boosters, the bar, the cube, the run, and so on. And for each one, you have a set of PCBs, a PCB 145 by 130, even 30 by 30, 50 by 50 by. So a huge variety. In this case, we are selecting the 145 by 130 millimeter. So we bring to the software without any matching network. And let's plot the impedance. You can see the impedance in the Smith chart is very far away from the center in the low frequency region, as well as in the high frequency region. It's totally mismatched. But this is not an issue at all, because we can design the matching network to have good matching and good efficiency. This is the flexibility of virtual antenna. Now we select the frequencies. We have the user manual that explains all this in case you want to use it. This library is step by step how fast, systematic, and easy is to use this library. In this case, we are selecting 7 components for our matching network, but you can say, well, I don't want more than 6 or 5. Well, then the software will say, well, with 5, I don't have enough, I need more. So you can play. And now we are defining the target. I want for this S11, and in this frequency range, I want my S11 to be below -6 dB. So you can specify as many targets as you want, 2, 3 frequency regions. In this case, we have 2 frequency regions. We optimize, and we are requesting the software to find a matching network, the topology and the values. It takes less than 2 or 3 minutes. It's very fast. So the software is working for us. Even you can take into consideration real components. Now we are using ideal components, but the optimization can take real components for any vendor, so with real losses, okay? Okay, this is done. You can see here we have cost 0. It means that we have a matching network with 6 components This means that the software find a solution. So let's see now without matching network and matching network. You see 1, 2, 3, 6 components in less than 3 minutes. And let's compare without matching network and with a matching network. The S11, you can see here now in blue. Okay. You see here in blue, it's the S11. It's not match in the low frequency region. It's very poor match, as well in the high frequency region. It's very poor match. But once we plot the S11 with the matching network, you can see that now we have very good performance in the low frequency region as well in the high frequency region. And everything has been done automatically without human intervention. It's very, well, it's fast and it's systematic and it's easy. It's easy to design from single band to multi-band for your IoT device. So this is libraries, very convenient if you are at the very beginning of the project and you want to determine which is the best size for your platform. Now we have other tools, the same software cadence and even obtaining in case you are in the lab with your device fully populated with your batteries, your plastic covers, with your antenna booster, and you want to design the matching network with the software ready to be implemented. So again, the process is very similar. You need to do some testing with S11 without matching network, bringing to the software and asking the software to optimize your impedance and providing the real components from vendors. And once you have these components, just you put it on your device, and most of the time without fine-tuning, you will have very good performance. We have a full-time 1-hour session that explains step by step how to address this. And again, it's very simple. It's very systematic because everything is done with the software in automatic fashion. And finally, for those using CST Studio Suite, the 3D EM simulator, now we have all of our virtual antenna products available in our web page throughout the encrypted models. So you can use it. They are in our web page. And let's illustrate, for instance, the trio. You have on the left the real product, and on the right, this is the encrypted model. So you have the same logos, the same part numbers, the same materials, the same geometry inside. Everything is encrypted. But at the end, you are going to use like an amplifier or a filter. You don't care what's inside. At the end, what you want is an amplifier with 20 dB gain and a figure of noise of 1 dB, period. And what's inside, you don't care. You use the component. The same happens here. You use the component, and you can put on your device, in this case, let's illustrate with the Thingy 91, which is fully populated. In yellow, we have the ground plane. In green, this clearance area, place for the SIM card, the transceiver. Even you can model the battery, and you can do your own stuff. And with advantage that now you can import into your software our antennas. Any kind of virtual antenna products can be imported, and well, you can design and do your own parametric analysis, enlarging the ground plane, putting the battery in one place or another place, and at the end optimize the performance. Let's move forward the video. You will see here the real product, and you are able now to simulate S parameter, design your matching network, take the efficiency, radiation parameters, and all this kind of stuff. Okay. And in those cases where you don't have perhaps the expertise or you don't have time to address that design, well, we can do it for you. Either if you are proof of concept, if you are in the design phase, or even if you are in qualification and you need to fine-tune the antenna system. We recommend you this service. It's a 24-hour service. It's free of charge, where we provide, usually in less than 24 hours, a report that contains, based on your specs is, well, my PCB size is 60 by 70, and I want to have operation in these frequency bands of narrowband IoT. So in return, you will receive a report containing which is the base antenna booster, the position, the simulation, the bill of materials of the matching network, so you can do your own analysis and even the results of efficiency, and you are able to take action at the very beginning of your project. So this is very convenient. Have a look at our webpage. If not, you can scan the QR code, and it's very easy to use this wireless fast track service. And just to conclude, let's have a look with virtual antenna compared with flexible printed antennas, based on feedback of some of our customers that they want to also use these antennas. Well, the issue that we have also analyzed very deeply is that when the flexible printed antenna is off the PCB, well, results in terms of bandwidth and efficiency, they are pretty very good. The issue is once the printed antenna is on the device, and the device has metallic layers, the ground plane for sure, and this has a very strong negative impact on the performance. In this case, we are comparing the total efficiency in the same platform size for the same frequency band of operation. In this case, we are using the RAN MX10. It's only 12 millimeter. It's more than in length, more than 10 times in length. This is about 90 millimeter by, I would say, 20 millimeter. It's very large footprint. And we have compared with several heights, from 2.4 millimeter from the ground plane up to I would say, a not realistic device. It's 20 millimeter. This is a very thick device. But anyway, in all cases, you can see that the efficiency in the low frequency region, covering most of the 700 to 960, the efficiency is pretty very low compared to the virtual antenna. No matter if you are using the thick case, for the same height, which is the yellow, efficiency is 50 times less. So now we understand the complaints from some of our customers when putting the antenna on the PCB. In the high region, this is not as critical, but again, you can see that always the virtual antenna gets very nice performance across all cases. And again, if we compare with the same height, the efficiency is not very good. But this is not only the issue with this kind of technology. We also detected that depending on the position that the mounter of the device has to, when it's in mass production, to place this, if the position is not predetermined, or perhaps it can be moved all around the device, you can get very different results. In this case, you can see in the red color, we can get from 6% to 10 times less. So depending on the position. So this is an unpredictable performance, which does not happen with virtual antenna. Virtual antenna, once the component is fixed, it's attached, because it's a pick and place component, it's soldered on the PCB, the behavior it's ensured. It's a predictable performance, which is very convenient for mass production. So to sum up, first steps, as in the chess game, it's very important to consider the antenna first. They are very simple steps, but in order to get efficiency, battery life, range, connection, consider the antenna from the very beginning. The position, the type of antenna booster, also the PCB size, and the matching network, and the position on the transceiver. In this case, the Nordic Semiconductor transceiver should be very close to the matching network. As a rule of thumb, less than 5 millimeter. If it can be 0, it's much better. Virtual antenna is unique, and it can operate for any band and for any device. We as designer, we can freely choose the frequency bands we want to operate at. It's 10 times smaller than any other chip. It's an off-the-shelf and pick and place. You have some electronic design tools that you can use for your own services, for your own designs. But if not, you have Ignion on your side to support and to accelerate your innovation. And you have seen some tips, some examples on how combining a virtual antenna together with Nordic Semiconductor transceiver, we can go from IoT multiband, also for IoT multi-radio, combining narrowband IoT, LTE-M, GPS, and all these kind of protocols, Bluetooth, Thread, Zigbee for any IoT device. So from Ignion side, Nordic Semiconductor too, thank you very much for your attendance, and we hope this webinar has been useful for you.